Hello class 12. As you can see, written on the board and drawn on the board. Okay, the topic that we're going to deal with today is a transformer. Not the transformer in the movie, okay, about the aliens, okay, robotic aliens so to say, but a transformer which can either increase or decrease the alternating voltage. Alright, so looking at its basic construction, what we have is we have a primary coil and we have a secondary coil. Okay, now these two primary and secondary coil can be wound over or is generally wound over a soft iron core. Okay, so these two parallel lines depicts the soft iron core part. So Vi is the input alternating voltage, of course. You can see the sine wave over here, the quark. Okay, and this is your output resistance or output resistor, so to say. Basically it's called the load resistor. Now whenever we use the word load for a resistor, what we mean to say is it's a very high value of resistance. Theoretically it should have infinite resistance, okay, such that the maximum potential difference can be measured across this resistor. The more its resistance, of course, more will be the potential difference that can be measured across it, and the potential difference that is measured across it is V0, that is the output voltage. Okay, now of course, as you already know, there can be two kinds of transformer. One is called a step up transformer, which increases the value of the voltage, and the other is a step down transformer, which decreases the value of the voltage. Okay, see, we have different kinds of transformers and different sizes of transformer in different electronic devices. We have a transformer inside the adapter of your charger also, mobile phone charger, your smartphone charger also. Okay, and of course you have transformers in different other electronic devices. Alright, so the first one is called the primary coil, the second one is called the secondary coil. As you can see in my picture, the secondary coil has more number of turns compared to the primary coil. So to say, what I've tried to draw over here is a step up transformer. In a step up transformer, we'll also see that in a step up transformer you will have more number of turns than in the primary coil, whereas in a step down transformer you will have lesser number of turns, okay, in the secondary compared to the primary. That is in case of step down, remember. Okay, so when we apply the alternating voltage Vi across the primary coil, what happens is, since the value of the alternating current goes on changing, and of course it goes on changing its direction after every instant, what happens is there is magnetic flux linked with each turn of the primary coil. Okay, now if we assume that there is no loss of energy whatsoever, or so to say, if there is no loss of magnetic flux, then if phi b be the magnetic flux linked with each turn of the primary, then if there is no energy losses, like already mentioned, if there is no loss of magnetic flux, then phi b will also be the magnetic flux linked with each turn of the secondary coil. That's of course an ideal scenario we are talking about, but still talking about or sticking to that very ideal scenario, if phi b be the magnetic flux linked with each turn of both the coils, primary and secondary, then, and of course, by the way, I forgot to mention, Np be the number of turns in the primary coil and Ns be the number of turns in the secondary coil, then the induced EMF in the primary coil will be given by Ep. This is equal to minus Np delta phi b divided by delta T from Faraday's laws, remember. Okay, the induced EMF has to be equal to the rate of change of the magnetic flux. Now since phi b, or rather delta phi b, is the flux or the change in flux linked with each turn of the primary, then the flux linked with the change in magnetic flux linked with the primary coil having NP turns is NP into delta phi B, of course. Okay, so this is what we get. Now, since we are assuming that there is no change in, or there is no loss of magnetic flux, then the EMF induced across the secondary will be minus NS delta phi B by delta T. Okay, I've made a mistake over here. This phi B is the magnetic flux linked with both the coils, of course. Each turn I should write phi B, not a delta. Delta represents the change in magnetic flux, remember. I haven't mentioned change over here. Phi B is simply the magnetic flux linked with each turn. I should mention this here. Each turn of both the coils. Okay, that will be more specific. So if phi B is the magnetic flux with each turn of both the coils, then delta phi B is the change in magnetic flux. Alright. So this is what we get. Okay. So dividing 1 by 2, or rather, if this is a 2, equation 2, and this is equation 1, dividing equation 2 by equation 1, we get ES by EP is equal to NS by NP. Alright, so the ratio of the EMF induced across the secondary to the EMF induced across the primary is equal to the ratio of the number of turns in the secondary to the number of turns in the primary. Remember that. Okay, so can I write, not write, can I erase this right hand side? I believe you've copied, so let me erase these things. Now again, since we are talking about a theoretical scenario, what we assume is, since there is no loss of energy whatsoever, so what we consider is there is no resistance of there is no resistance in the wire that makes up this coil, so to say. So if there is no resistance, there is no loss in energy in the primary. So if there is no loss in energy in the primary, then what we have is EP will be equal to VI, the input voltage. Okay, that is the EMF induced in the primary will be equal to the input voltage. And likewise, if, like I already said, RL, the load resistance, is a very high value of resistance, almost infinite, theoretically infinite, of course, then what happens is the EMF induced across the secondary will also be equal to the output voltage. Okay, of course, these are theoretical scenarios we are talking about, remember, because the wire that makes up the coil will have some resistance of its own. However smaller value it be, but it will have a resistance of its own. So obviously there will be some loss in energy, remember. So if this is the scenario, so from here we can write therefore V0 by VI, okay, dividing this by this, we get is equal to ES by EP, which is equal to NS by NP, and this is what is denoted by a small r. Small r itself is called the transformation ratio. It's called the transformation ratio. Okay, now for a step up transformer, R will be greater than 1. For this is for step up transformer. Whereas for a step down transformer, R will be lesser than 1. For a step down transformer, remember that. Step down transformer. Okay, of course you can make out from here itself. If R is greater than 1, then the number of turns in the secondary will be greater than the number of turns in the primary. Whereas if R is lesser than 1, then the number of turns in the secondary will be lesser than the number of turns in the primary. Okay, the criteria I mentioned earlier for step up and step down transformers respectively. Alright, okay, so do remember this important relation, so to say. R is called the transformation ratio. Okay. Likewise, now, if IP and, or let me write it this way, if IP be the current in the primary at any instant in the primary, and likewise IS be the current in the secondary coil at that very instant, remember, in the secondary. And what we are already assuming is, we are assuming that there is no loss in energy whatsoever. Okay, so I believe I can erase this part. So since we are considering an ideal case that there is no loss in energy whatsoever in this transformer, so therefore the power in the primary has to be equal to the power in the secondary coil, remember. Alright, in the secondary. So to say, what is power? Power in the primary will be VI into IP. This has to be equal to the power in the secondary, which is the output voltage measured by, multiplied by the current in the secondary. So to say, therefore, V0 by Vi is equal to, V0 by Vi will be how much? Will be IP by Is, and this of course is equal to the whole thing over there, which is Es by EP, which is Ns by Np, which is equal to R. Remember that. Okay, so we have one more equation, one more relation regarding the current, one more ratio involved with the transformation ratio itself. Now, this is an ideal scenario that we again considered, remember, that there is no loss in energy, hence the power in the primary coil has to be equal to the power in the secondary. Using this equation, there are numericals given, remember. Okay, so do not forget this important equation or important relation, of course considering an ideal scenario for a transformer. Okay, now what can we learn from this equation? See, if we are talking about a step-up transformer, okay, now in a step-up transformer, obviously the voltage, the output voltage is increased to a higher value as compared to your input voltage. Now, voltage or potential basically is work done, or basically it is energy. So to say, in a step-up transformer, we are increasing the output energy, so to say. Now, get this thing very, very clear. Although, so to say, the output voltage, in a step-up transformer, output voltage is increasing, or so to say, the output energy is increasing. A transformer does not violate your conservation of energy, remember that. Alright? Because you can see, as the output voltage increases compared to your input voltage, what happens correspondingly, the current in the secondary decreases when the output voltage increases. So when there is an increase in the output voltage, the current in the secondary correspondingly with the same ratio, of course, alright, following the same ratio or corresponding decrease in the secondary current happens when the output voltage increases. Okay, so this transformer is not violating your conservation of energy. Get that in very, very clearly. Okay, so this is about your transformer. Now there are, we considered ideal scenario every time, of course, but like I already mentioned, there are energy losses in transformer, and there are different kinds of energy losses, like copper losses. Let me write that for you. I believe I can erase this. Let me discuss that point also. So energy losses in a transformer. Number one is called copper loss. Now what is this copper loss? The wire generally is made up of copper, of course. Now, like I already told, whatever conductor or whatever metal the wire may be made up of, the metal will have some value of resistance. Okay, so there will be loss of energy through that resistance in the form of heat, which is called copper loss. Number 2, of course, there will be eddy loss. Let me call it eddy loss. Okay. Now, what is this eddy loss? We have a soft iron core in between the two coils. The soft iron core, of course, is made up of a conductor, and all the while what happens, the magnetic flux linked with the conductor is changed. Now, when the magnetic flux linked with the conductor on the hole is changed, eddy current is generated in the conductor. And we've already discussed eddy currents. Whenever eddy current is generated, it also produces heat energy. So, there is loss of energy because of eddy current also. Alright, now to minimize eddy current loss, what is done is, you don't use a solid soft iron core conductor. What you rather do is, you use laminated conductor, soft iron core. Now what is that laminated? You take thin sheets of, different sheets of the conductor, and you paste them together such that they are insulated from each other. Alright, so what you do is, you use a laminated soft iron core such that since they are insulated from each other, the eddy current, of course eddy current is generated, but the value of eddy current generated is not much, is not of a higher order. Okay, so that is how eddy current losses can be minimized. Number 3 is hysteresis. Hysteresis, hysteresis loss. I forgot the spelling of hysteresis, I believe it's this. Okay, so hysteresis loss, what is hysteresis? It's a process of magnetization and demagnetization. So all the while magnetic flux is linked with, or is changed with this soft iron core, this soft iron core goes through a process of magnetization and demagnetization, because of which this soft iron core obviously generates heat energy. And obviously energy is lost in the form of heat, which is called hysteresis loss. Alright, now these are the 3 basic energy losses in a transformer. There are other kinds of losses also, alright, but you can give it a look. So we stop here for the transformer. Do not forget this. Thank you.